to je to. Nisam dugo streamao, valjda bude sve ok. Evo, dobro, zeleno je. To jest ne znam uopće da li sam streamao od kad imam optiku. Excellent connection, to volim čuti. Evo, a sad ćemo u biti vidjeti, malo on sporije, nakon nekih 30 sekundi on pokaže šta se stvarno dešava. Pa ćemo vidjeti sada.
Ali sad bi bilo dobro šta, da se prebacimo na engleski.
Pa dok dođe prvi čovjek.
Aha, još ni nema nikog.
Ima samo... Okay, hello everyone. Good to see that the live function is still fully operational. It's been quite a while since I've actually done a live stream. But what a better way to get back to it than by having a wonderful conversation with not one but two physics PhD gentlemen. What's the exact term that you can use?
Theoretical physicist.
Yeah, I would say theoretical cosmology
and astrophysics.
Theoretical cosmology and astrophysics. All right, here we have...
I'm more like cosmology, he's more like astrophysics. If we need to divide.
Dr. Petar Pavlović and Dr. Andrej Dundović. Dundović has already been here on the channel, I think at least once.
Once.
Was it only once? Yeah, okay, once, and it's Petar's first time. And the way we did it the first time was that we discussed a few topics, and then you guys, if you had any questions regarding pretty much anything in the universe,
of course.
You can ask a question, and they will do, I think, the best they can to answer it properly. And while we are doing this, in the background we will have the Universe Arena, as I've prepared it. It starts in 29 minutes. So up until then, we're gonna be discussing many great things. So just to top it off, the top 10 currently are Stephen Willie with 2522 rating from the United States. I've even played him once, 5 times. I actually won a game and lost 4, so that's fine. Then Silly Boy, Ratahmas, okay, I can't even read this, but P-Chess, the Megash Kumar, Varat 45, I think we've played quite a few games, 14 games to 6. Epic Finisher, I'm still in 8 here, but I will withdraw as I will not be playing. Then we have Christo, Shreyas Kingdom 981, and Dario Nunes. So those are the top 10. Currently 165 players in the tournament, and more are joining in. So, gentlemen, once again, it's a privilege to have you here. What's currently the, at least that's what I always like to ask, what's the hot topic in your field of specialty?
First, thank you for inviting us.
There we go. You can be a little bit louder. I don't know if everyone can hear you, but we're gonna see that in a second.
Well, I mean, will you say first for cosmology, and I'll take the high energy astrophysics?
Okay, I mean, I can be quite simple because the most
don't say nothing.
Yeah. Okay, I'll say something at least, but you know, the hot topic is actually the universe itself, because actually we didn't come that much closer to understanding it in its totality, in its past and its future, and the way how does it functions fundamentally. So all these great questions that we had as a humanity from the beginning of the first speculations of man related to nature and his position in nature are still open. So, and this is always equally interesting and fundamental and hot topic. So it's a a complete evergreen.
Yeah, we haven't come much closer.
We of course we did. Hot topic. Yeah, it's a hot topic because you can never actually exhaust the topic. You always do some steps. You always break some complexity into some separate parts, but then you actually find even more complexity there. But what is fascinating is that at each step you actually find more and more clues pointing towards the unity, so that there is the underlying unity in the structure of the whole reality, the universality of the physical laws, the connectedness of all scales, that actually the cosmos, the universe, is actually one single whole, That's the most fascinating thing. The things get more and more complex and complex, but also at the same time you find more and more unity in this complexness. So that's how it goes.
And in your field of specialty,
I would say that, so all these troubles with fundamental physics as problem of dark matter, dark energy, these are still topics that people are for years and years trying
still the big topics.
But I think that, for example, what's changed in last, let's say, 6-7 years is the new method of observing the universe through gravitational waves. So that is something that brought some new empirical data, and from that there are a lot of also new theoretical speculations and insights. So I would say that there are some topics that are constantly covered, but this is something which one should definitely highlight.
What okay, you don't have to go into detail, but what does it actually mean observing the universe through gravitational waves?
So we have the real problem with our empirical researching the universe is that it's so big. Okay. Actually, you cannot
unimaginably big.
Yes, and you cannot even.
Perhaps even endless.
We cannot even exit our solar system. Solar probes like Voyager 1 and Voyager 2 are traveling for more than 50 years, and they're just exiting the heliosphere. And you can imagine that we cannot even reach the nearest star. So in that sense, the only way to get to harvest empirical data is through observations. And we are using electromagnetic spectra for now a few hundred years, while in recent years there are new ways to observe the universe, and one of the most prominent now is the observing through the gravitational waves. So that is something that Albert Einstein predicted.
Like you don't have to use photons?
Yes, so you're detecting distortions in space-time, and through that distortions you're trying to see where these distortions are coming from, these signals in form of distortions, and you're trying to model what produced those gravitational waves. And what we now are assuming is that all these gravitational waves that we are detecting are coming from black hole mergers or neutron star mergers, or combination of black holes and neutron stars. So these are something that is completely new way of looking into the universe, and that is bringing some empirical data from which you can deduce how, for example, how often these mergers are happening, so, and all this type of indirect conclusions. So I think, and also what is also a hot topic is to observe the combination of one event in multiple channels with multiple messengers. So for example, gravitational wave observatories are detecting from one direction a gravitational wave, and then all other observatories, cosmic rays, neutrinos, or radio, or optical, they're all looking into the same direction to see if something else would also come from these directions.
I would just like to add, from a point of view of general relativity, that gravitational waves are actually quite a fascinating thing. And I think quite often in popular science, it's not represented actually in a very precise way how we should view this phenomena from the actually fundamental perspective of general relativity, it's not like you have something which is propagating in the space-time, as all other types of propagations are actually propagating. It is the very space-time which is fluctuating. It's not like you have some sort of message traveling through space-time, and then the space-time would just be completely background independent and just stay as it is. The gravitational waves are actually the very oscillation of the structure of space-time itself. So it's not something traveling on it. It's actually the very space-time structure which is oscillating.
But what are what's the actual information that you can get through gravitational waves that you cannot get from traditional means of observing the universe?
So you can compare this with, I mean, with our senses. You can see, you can smell, you can hear, you can touch.
But there's
and so there are different experience. So if you see something,
but it's like
better. For example, if you're drinking fine wine, it's better that you smell it and taste it and see it at the same time.
Okay, and it's probably with those 5 senses you can maybe taste 5% of the universe, and then with this maybe you can taste maybe a larger chunk.
Also, like for some cases, like the early universe, in the very early age of the universe, it was not transparent to electromagnetic radiation. So all this cosmic microwave background spectrum, it's actually not, when they say, you know, like the first light in the universe and so on, like the Big Bang signals, it's like 300,000 years after the supposed moment of Big Bang. So if you want to penetrate deeper somehow with some probe, in the earlier periods of the universe, you cannot use electromagnetic spectrum. So the gravitational waves are the only type of signal from the early universe that we could get. So in some cases, it's the only type of signal that you can actually try to catch and deduce something out of it.
All right, so we're gonna be discussing a lot more, and we will, yes, as I've seen some of you have been asking, will we also be taking questions from the audience? We will, but as here in my hometown, as it is also Andrej's hometown, Petar is visiting us from the capital of Croatia, from Zagreb. A observatory was built, or what's the correct term for it?
Okay, so we built a building which we call the Cosmological Center.
Okay, the Cosmological Center.
And a part of it is astronomical observatory.
Okay.
So the idea is not to have the best observatory in the world, the biggest or something. There are better places for this kind of observatories than in our hometown. However, the idea is to represent that on this place we are studying the universe. So that there is no better symbol than having a real proper observatory.
And what we want to combine is actually doing science, the place for the research of the universe, primarily theoretical, with popularization of science, bringing science back to the society, teaching like cool. Students and high school students, or the people who are interested, who want to learn and who want to hear from the first-hand experience what's new going on in science. So that's the idea, to have a single place dedicated to universe, which is not just a place for popularization, and it's not just a place for doing research in science, but is actually a place for both at the same time. That's the idea.
And
you are also, from time to time, I understand, teaching children or younger people of different ages.
Well, sometimes we have different programs for both students, high school pupils, and sometimes we even have programs for younger ages to visit the observatory. I mean, it's a cool experience for kids who never been under astronomical dome. And it's always like a really nice direct experience of a place where you can study the universe.
I mean, I can imagine. I'm 35 and it's the first time I've been in an astronomical dome. You know.
And it's cool.
Yeah, it's really awesome.
Cool.
Yeah, and we are we do have some photos of it, so we're gonna check it out now.
Okay.
All right, so let's check out this
because the
incredible place.
photos are saying
Yeah, and you guys
more
can
than words.
talk a little bit about the photos. So just to have it prepared, there we go. Let me just open this up. There we go. All right, so let's hear it.
Okay, so this is the building. It's so Križevci are not a big city, so the building is not oversized in a sense that it has 2 lecture rooms, it has some offices, and also at the top there is a astronomical dome with the observatory. So you can.
All right.
Okay, this is
This is a view through the dome, yeah.
Yes, this is some. I took this photo. This is Jupiter
and Moon, huh?
And Moon and Venus.
Ah, Venus.
Yes.
All right,
okay.
so there we have it.
Yeah.
A very nice, clear photo of Venus. What's that? What's that below?
Below.
All right. This is
Okay,
maybe.
this is during the daytime.
Yeah. Okay, so there we have the opening and the dome itself. It has the full view of the night sky. Yeah, the 180
Yes,
view.
it rotates.
Yeah, it rotates.
360 degrees, so that you can observe the whole half of the sphere.
Okay. All right. This is a view from a different source. There we have it. And this is the what can one expect to find here on the upper floors?
I mean, this is a nice. Sometimes here we have, for example, last year we had a summer school on the top here on the first floor under the open sky, and also here we can put also smaller telescopes to observe the night sky.
Yeah, I've been there.
And
you
also
had like 3 of them.
The sun. It's also nice to see sunspots. And
Yeah, there's a nice photo of it at night time. Also from the front. There you have it.
Okay, these are. So here you can see the city in the background.
And this bad boy on the left, that's the telescope, yeah?
Yes, that's. So it's a nice telescope. It's not something super expensive or something, but it's something that you need.
Is this photo taken with the telescope?
Yes, but it's still. I mean, I think that we can do better.
Okay.
But this is from our testing, just to.
Okay. Better, you mean in terms of clarity or in terms of seeing deeper?
No, you can see also deeper, but
both actually. Yeah. But
both.
here clarity is issue.
Okay. Yeah. All right. There we have it. Another angle. There you actually see the lens.
So the idea is why we made the building so all whitish without too many details and without too many windows is we wanted to achieve this effect of monument, so that it looks monumental and that people are more attracted to it as a symbol, not as some kind of normal functional building. So it's without too many details, so that it can enhance the observatory, and so as you can see, I mean.
Yeah, it really stands out. It's the nicest one in the city. There we have it. Another one from this angle, also from this one, very nice.
And people are always surprised how it's much bigger from the inside.
Yeah.
Because because of the circular form, you always think that it's from the outside it looks smaller than from the inside. That's nice.
Yeah. Okay, we've had this one. This is the magazine, yeah.
So this is the journal. So actually it's a complementary thing somehow, because this observatory is mostly made for the wide audience and this
outreach.
for the outreach purposes. But the journal is actually a scientific in form, and it focused mostly on theoretical physics and philosophy of nature and philosophy of science. So it is an academic journal. So in some sense, I say they are complementary because, you know, the observatory is something physical, something material, something visible, and this is okay. It is still physical, but the essence is what is written, the idea, no? And this is again for the specialized circle of the audience, and this is for the more wider audience. So somehow those two things, the journal that we saw the picture of and the observatory, are actually two pillars which represent what we did so far. So the you know, what's the field in which we are trying to do our thing. So what are the coordinates? So they are spread between those two pillars.
And I would also emphasize that the great thing about this building and the Cosmological Center is that a lot of people engaged into this. So we gathered different institutions and public institutions, and also non-government organizations, which are all participating in this. So it's not only that Petar and I decided that we will build here, like he took the hammer and I took. So there are a lot of people engaged, and actually, so people never thought that they would participate in something that is related to the universe. It's like people are always looking around. What should I do today? I need to go to the grocery store. I need to go to the doctor. And then you stop them and say, wait, let's look above. Let's take a look on the stars, and let's try to build something that you maybe asked yourself when you were young, but then you forgot maybe to ask big questions. And that's why we build this to pause people a bit, and so they from their regular lives, and so they can join in fundamental questions.
Yeah, it's always you know, you're in a hurry to finish a project when, you know, our entire galaxy is like spinning towards the unknown at what speed, at like 2 million kilometers an hour or something like that. It's you know, if you stop to think about that, then okay, your project doesn't seem all that big of a deal. But
we need more of that perspective. We need more of the cosmological perspective in our daily life. Because then we realize actually how stupid and insignificant all of this is, including our lives. And this is actually what
is that a good
cosmology.
thing?
That is what cosmology can teach us,
like, you know,
to see that, you know,
people are walking by and you are meaningless.
Then if you put things in that perspective, then you can you know, actually rise above your ego and your limited desires and your limited conditioning, and you can just be more relaxed and not give a damn for these things that you are actually experiencing. So actually it's also you look at the stars, but then they also teach you something. It is not just that you are passively looking and do not receive anything back from it.
Is that a good trait to have early in life, or maybe adopt later on? Maybe
I think that through whole life you should
bit by bit in different ways.
Yeah. All right. And what's the interest, for example, of younger population for physics, for astronomy, for studying the, you know, the
I mean, it's a good thing. Maybe Petar, I didn't tell you, but now kids here in Križevci are saying that they want to be scientists.
Oh yeah.
Really?
Yeah, so that's a good thing. We are already making something out of it.
Seriously, where did they say that?
No, they said it in schools when they returned from the.
But when you deliver few lectures with mathematics and equations, then the enthusiasm diminishes a bit. But still, you always, I think, in every generation you have few of people who are able to do actually even mathematical analysis and calculus even in the high school in the early grades. But they just need somebody who has time and who can give the proper motivation and relate all of this with the universe. The big problem is if you don't get actually some motivation, why you would practice, study, do all the math, and it can look quite dry on its own. But then if you explain that it's a tool, you can do great things with it, then it goes much easier.
Yeah, like look at these two gentlemen. They know math and they've built an observatory. So
you need math to build an observatory.
You saw that angle. We were calculating the angle, so that
very nice angle. Yeah. Yeah, so maybe nowadays being sort of into science is the new cool, because I don't know, some 20 years ago when we were in high school, most people were smoking and drinking. Maybe now people.
You always have people who will smoke and drink, and some other who will be interested in science.
No,
but I think maybe now
it's maybe now it's.
I mean, but maybe it's also a trend. It depends how.
We need to wait and see for 5 years at least, and then we can determine, what the tendency.
Statistically significant in the long run.
Do you think the advancement of technology in the world goes in favor of popularizing science with children or against it, for example?
No, I think. May I answer this? So I think that the problem is that we should keep the popularization of science with simple concepts, not to give too complex stuff, because I mean these days all this advanced technology looks like magic. I mean, there are some buttons, but you don't understand how it works.
Yeah.
And it's a problem. I mean, it's better to have bricks and to understand what these bricks do, and to build something with that conceptually when you're in young age. Then I don't know, give some robots that are activated by voice or something. It's just too. I think it's too early for kids to get access to advanced technology, because, like, who said that there is no difference. Who does not understand there is no difference between technology
and magic.
I think it was
pretty much everyone who thought about anything at any point.
I think that the people in the.
Oh no, I've heard it like a million times, but I have no idea who said it. But yeah, it's essentially if technology advances to a certain point, it is indistinguishable from magic.
Yes,
and if you don't have control and understanding of the basic principles, that's the essential thing.
That's why
you need to first have the grasp of the fundamental principles, and to be able to follow at least, in some rough. How do you get to
yeah, but okay, if for example we were able to teleport something, you cannot distinguish that from magic.
Of course,
no. But the difference is only in the fact that you can know principles and explain them rationally. Okay. That's the important thing.
Yeah.
And then quite often you have this tendency that it's idea to amuse people, but then this amusement can actually be stimulating to go to the understanding. But if you do not get to understanding, then you do not achieve much. That you're just at this level of simple magic.
Okay.
But the idea is just to use this effect, this magical, feeling of the whole thing to get to the understanding. And the understanding is what is essential.
Yeah.
Because then you can see that kids, if they understand what is going on, then they can show some creativity. Then they can readjust stuff and they can build new stuff. Well, if you give them some complicated things, they will just know how to use it.
Just push buttons.
Yes, but it is impossible for them to readjust that. They can only break this microphone. They cannot make.
Yeah, and they will never be someone who creates something better than this.
Yes, finally, that is the.
Yeah, and you since the observatory was built, you've had quite a few lectures, like I said, for for people of all ages. I'm interested in the younger generation. So what topics are they most interested in? Like what has the
Well, of course that the younger they are, you can you need to be more interactive with them, and you need to show them something more how to say that, more visible. So
okay.
in a sense that you cannot go a bit too theoretical. You cannot go into too many new concepts. So you just need to show them and adapt. The idea is actually to give them some flashes of what can be done, and there's some what is interesting, and of course that most of these things will be forgotten or will not be understood, but something will stick. So that is the idea. While for people who are like high school and older students, then you can be systematic and you can say these are foundations, these are assumptions, and we are building something, a system, and for with them you can do that, but with younger kids you cannot do that.
All right. So, what is in your opinion the most wrong thing about today's idea of how the universe works? Like if you walk down the street and you ask someone how the universe works, you would get pretty much a general reply. Do you have something that you would like to improve on that?
Petar, this
Okay.
is your favorite
Yeah,
topic.
could be, no? So I would say, the most problematic point probably is that people are still thinking in terms of the old mechanicistical picture of the universe that was once used in the 19th century, more or less. So you imagine that the universe is just like a big machine with different parts, and they are just affecting each other, and it's all completely deterministic and subjected to just mechanical forces. So, and this is actually not how things are, because this whole worldview was rejected by quantum physics and by general theory of relativity. So instead of that, actually, we have a new worldview in which is in accord with quantum physics and with general relativity, in which everything is actually inseparable and interconnected, in which everything is more free and has this internal movement and spontaneous nature and possibility to evolve in different directions, which with associated probabilities of its all. So it's so the thing is, to put it briefly and more simple, I think that the universe is not just like some machine which is operating mechanically,
Like
but
a clock,
it is more like a spontaneous movement and dance and interconnection of all parts. It is much more psychedelic than just dry realism going on there. It's much more beautiful actually than most of us think.
So that's the biggest problem, yeah.
But I think that would you also refer to the early universe?
Yeah, also okay. Okay. I mean, there are many problems, but also one of the biggest problem is that people assume that we know how did the universe begin or how it will end. So this is completely actually unknown. I mean, the idea that there was a beginning of the universe and initial singularity comes as a result only of the general relativity, and this theory is actually not necessarily correct on such high energies. We assume that there should be some quantum corrections there, and we don't have the complete theory for this early universe, which would actually say what was going on. So it's all actually speculation. We don't know what was happening in the very early universe. We don't know actually what's the exact composition of substances and tendencies operating in the universe today, and we don't know actually how the future of the universe will look like. So there are different probabilities, different models, even according to our own to the data and theoretical setups that we know today. And we also need to be open to the fact that probably in the future the new horizons will be opened. No? So actually, in this, people want to know, they want to have fast answers to the very fundamental questions, but we don't actually, we are not near to answer those questions in this moment. So the thing is that some theories which are not complete and which cannot be trusted in those regimes are giving some answers, and they are just accepted as the science says it is like that. And it's not necessarily so. So maybe there was no Big Bang, maybe there was a cosmological bounce, maybe there are the epochs of the universe which is just contracting and expanding and so on. So all these possibilities are still open, and the fact is that we don't have a proper theory of gravity, which would be a quantum theory of gravity, so we don't have the full grasp of all those high energy scales. So actually it is much more rich, it is much more dynamical, it is much less mechanical and simple, the universe, than we think, but it is also much more mysterious than we think.
Unfortunately for
Peter. I need to go soon. Yes, to catch a train.
Yeah, Petar actually needs to catch a train that he's
and
going
there is
on.
the video also, if you that we
Of the train?
No, of the observatory. And if you forgot, I don't know, maybe you did not. I'm just reminding.
No.
Yes, I forgot.
You
yeah,
forgot.
But,
Okay,
yeah,
I had the idea.
we will play it at some point. Yeah, I tend to forget stuff.
Okay.
Yeah.
Okay.
But yeah, I'm very glad that you could join us, even if so briefly. And
thanks.
we will.
It was nice. No,
yeah,
thanks for
we will try to
inviting me.
repeat this, fairly soon. To make it like a proper, maybe 2 hours or something.
I will be glad to come always.
Yeah. Okay. Things. So much stuff is happening in physics. I mean, we will have much to discuss.
Yeah, I think. Yeah.
All right. So I will show you.
Okay.
Yes. You have everything is set, and
I'm
Andrej,
not catching the train, so I'm staying.
Fair.
Okay.
Until next time.
Bye.
All right. So Petar had to leave us, unfortunately, but we are still here, and we will be taking some questions from the audience. Let me just see if we can improve a little bit on this. All right, this is perfectly fine. Let's just go back here. Let me just throw a game in the background. All right, here we have a gentleman already playing. All right, so we do have some time for a few questions, and then we are going to. Hey, thank you, Mr. Salo, for gifting five people memberships. Wow, what a true gentleman. We do have time for some questions. Probably some of you have asked questions. I just wasn't following the chat. So if you guys are still here, feel free to repeat some of the questions, and we are going to go over them. Let me just check real quickly.
Okay, let's see.
What do you think about what Pierre Denis wrote?
Okay.
Quantum physics and general relativity are all right to comprehend on their own, but the effects of considering them together always made my brain explode.
Well, I think that the most interesting first thing that when we are discussing this is that we know that both quantum physics or quantum mechanics and general relativity are doing great in terms of predicting and comparing with empirical results. However, they're conceptually totally different, and so it's not only to unite them. It's you need to change the own concepts for them to talk. For example, in quantum physics, everything. So you have interactions, basic interactions between fundamental forces like electromagnetic force or weak nuclear or strong nuclear force. And here, of course, when you have thing like gravity, you would call it also a force. However, in general relativity,
It is not.
It is not.
Yeah.
It is not a force. It's it's a consequence of distortions of or warping warping the space-time. So in that sense, it's totally different concepts. And so what physicists cannot agree for like decades now is on which side should we go? Should we decide that gravity is actually an interaction and that you have some mediators like graviton, which are
you have to find the particle first in order to say you are a force.
Yes, you need to introduce this concept then that gravity is a force and that you're looking for some particle or particles that are mediating this interaction. However, if it's not a force, you cannot find particles. Or I mean, in that sense, it's something different. And what should you give up of general relativity and that beautiful merge of space-time and matter in all geometrical theory, or should you stick with quantum mechanics and field theories, which are saying something conceptually different? So for years, I think that the dominant force in physical community is to try to quantize gravity. So to bring general relativity into the camp of quantum mechanics and to use these terms. And also there are some other approaches. For example, Einstein was until later in his life, he was trying to make other interactions more like general relativity, like electromagnetism. And so these two approaches are, we cannot decide. But I think that it's hard to ignore the achievement of general relativity in terms of basic idea. So if you say, if you drop this idea of of curvature of space-time, then you're leaving something really, really nice to join the general, join the.
Yeah, you need to unite them with a completely new and fresh worldview.
Yeah, so I think that what we need to do is to find some new ideas, new terms, which should share both origins, but which, for example, like in quantum mechanics, we united particles and waves. So there is no a particle or a wave, but these two concepts are united in a particle wave nature of both matter and fields. However, I think that we need to bring also those unification of those concepts from general relativity and from quantum mechanics, and that is hard. I mean, nobody still did it.
Yeah, but also I don't know, if you're driving from your place to my place, you're not going to use quantum mechanics to describe this trip you've made with the car.
Yes, I mean actually we landed to the moon with Newton's gravity. So it's, you don't need those advanced theories for like general relativity. Okay, they say, for example, that general relativity is important for global positioning system to work, for navigation.
But it really isn't, yeah.
I mean, it is. But I thought, when I asked people who are working on that, so I asked, we know that the closer you go to the center of gravity, that this gravity is distorting, curving the space-time. So that means that time is ticking slower the closer you go to the center of gravity. And because of that, the time ticks differently on the surface of the Earth and in the orbit.
Yes, your feet are much younger than your brain.
Not much, but,
but you know,
few milliseconds.
Yeah.
Because we're like walking on the 2 feet. However, the problem with satellites, you need to triangulate your position on the surface of the planet. You need to take into account those different delays that are coming in signal. And some of these are coming actually from these delays
from the curvature,
yes, from the dilatation of time. And because of that, you need to take these corrections into account for the system to work. Otherwise, you will be 100 meters away, located away from the position where you are.
Car crashes will happen.
However, they're doing this only, let's say, brute forcing, in a sense that they're constantly synchronizing clocks and taking into account this drift. So there is no that they actually put complicated equations, which, because general relativity is really mathematically complicated to calculate. So they're not using really complicated equations to calculate this transition, but they just know that this drift is coming from general relativity, and they're correcting it numerically.
So, okay. So it's they're still using general relativity, just making adjustments.
No. So they know what is going on because of general relativity, but they're correcting it with pretty much something. I mean, I don't know the details, but I was surprised when I asked those people who are working on this that this is not the case. That they're just taking into account how in average this is delayed and how much it should be corrected, and then they do this correction without big math.
Yeah, okay. Something. But now that you've mentioned it, is there any where on Earth that we are actually using it? Quantum physics,
general relativity.
General relativity for everyday life.
Let me think. So the thing is that the planet Earth is really small in cosmic context.
Yeah.
So these corrections of general relativity are not so important compared to the Newton's gravity in the context of the Earth. And I think that
because the Earth is so small.
Yes, and so I mean the first you need to have some really, really tiny effects, something really precise needs to go on, so that this theory will kick in. Otherwise, I mean, it's only how they first confirmations of general relativity came from bending the light around the sun. That is done by on how it's called now. I can this British astrophysicist, astronomer Eddington. Yes, Eddington measured the bending of light during the eclipse, the solar eclipse. So he removed the sunshine of the sun, and then he observed the night sky, the stars, and he observed how much they shifted compared to the normal stars when they're not near the sun. And so he confirmed that this bending is due to the sun's gravity, so that light rays that are passing next to the sun are bended by the sun's gravity. and that is predicted by Albert Einstein. And so that was when Einstein became famous. So that is the moment where Eddington made him famous, because that was the real solid confirmation that these are not just mathematical speculations that Einstein did, but some real concrete prediction.
Or that's what made Einstein famous.
Yes, I mean world famous.
Yeah.
That is where he launched into orbit. I mean, he became the best known scientist ever, at least in 20th century.
Okay. So he had everything calculated, but then Mr. Eddington actually confirmed that it is so.
Yes, so that was, and also later other predictions and other calculations, like perihel of Mercury. These are something. So because Mercury is so close to the Sun, that also general relativity is making a difference here compared to the Newton's gravity. So only places where gravity is strong, you should consider general relativity. And unfortunately, or fortunately, here
yeah, we would not be having this conversation otherwise.
Yes. So, but compared to quantum mechanics, this is totally different. I mean, quantum mechanics is really relevant because, I mean, first we have these microchips where all these quantum effects are important. I mean, we wouldn't know about semiconductors if there wouldn't be if there is no knowledge of quantum mechanics.
Okay, here's an interesting question from a gentleman, not specifically considering physics, but also how you got to where you are. How did you deal with failure, discouragement in your career? Was there a time where you were thinking, "Oh, can I do this? Is it possible for me to do this?"
That is a tough question, but I'll tell you. I think that the hardest thing is actually, I think that most people who are going to PhD are having difficult time to go through this process. And the reason is that you're almost always walking through some uncharted territory. So there is no like exercise where you know the result. Maybe all your research and everything what you do will come up. You will not find anything.
Or maybe someone will dispute it the next day.
Yes, but also you cannot be sure because nobody did that. The idea of making a new research is to do something that other people didn't. And then trouble is, how do you know it's correct? You don't. And maybe you're making multiples checks and everything, but you're always uncertain, unsure, and there is this pressure because you need to finish this process, you need to obtain your PhD, you need to find some new results, and you cannot predict that. You don't know if you will find something or you, and then this is a pressure that is coming from the system of from academic system, is that you're on this track and you need to complete these tasks, but these tasks are not defined, so you don't have you don't know the exact results or goals that you should achieve. And also when you're doing this research, multiple new questions are coming up. And you are trying to look the answer, and all this uncertainty is making us anxious, and I think that this is the hardest part. And what you need to do in this sense, how do you come to alive from this process, I mean mentally mentally healthy, is that you say that the process is important and you should not try to fulfill those external requirements too much, because those external requirements are usually contradicting. You should do this, you should do that, and you cannot do multiple things in the same time. So in that sense, I believe that the hardest part is to realize that maybe you are right on something and others are wrong. And what you're learned, what you're educated from early ages, that in average more people
Are wrong.
are right. I mean,
right.
I mean, so when you say everybody are going this direction, why would you go the other direction? I mean, it's not natural.
No, that is what I meant. Yeah.
So most people are usually, what we are taught, are right. And here you need to make this distinction and say, okay, maybe here I'm right and others are wrong. And I think this is where we are start to either I mean, this is the hardest decision because it's contra our previous logic.
Yeah. I always thought that it was the same for every aspect of life. You know, I mean, if you wanna be healthy and look good, you know, you should your goal should be to fulfill the exercise, not the end result. And I think that in most areas of life where the majority goes, it often is wrong. I don't know. Everyone always takes the easy way. Everyone always takes the. So I don't know.
Yes, but I mean, you could see that. I mean, the outcome. If people are crossing some road and they survive this crossing, you would say, okay, they survived. And I'm not sure if this path where I'm going will bring me. I mean, you need to take a risk.
Yeah, that's a lot more basic than what I was going for. But yeah.
I mean, in essence, I mean, you could find arguments for both sides, but generally, when you are stressed, especially in science where there are so many unknowns.
Oh, sorry. Does someone at some point try to disprove your findings once you've published a PhD? Like actively? Is it?
Of course, I mean, disputes are natural in scientific community. I mean, it's wrong to have this idea of a science of some temple where everything is in harmony, everybody are talking.
Yeah.
I mean, there are constant disputes, and people disagree with different groups, different researchers, different concepts. They disagree constantly, and you need to build arguments, and of course you need to listen the arguments, because you're always improving. If somebody criticizes your theory, your result, you can always improve. The worst thing is that nobody cares.
Yeah.
So that is the worst. When completely everybody ignores your papers, and then I mean.
Okay, but then you have to actively choose a hot topic.
Yes, that's true. But still, on the other hand, there are many problems in physics where you need some time to get into it, and years of research. For example, I'm starting to study the problem of turbulence. I mean, this is a problem that took
one of the unsolvable problems of the universe.
Yeah, I mean, it's just to introduce this problem. Why? So that the audience know. So really, this problem occurs in fluids, or for example, you could see it in water when you're opening a tap, a pipe. Then you see that when you're increasing the flow, it changes the color. So first it's transparent, and when you are opening mine, it's becoming white. And that is the transition, what we call from laminar flow to turbulent flow.
Mm-hmm.
So, and what is happening? There are many vertices and eddies are occurring during more rapid flow. and that is creating what we said a turbulent flow. And
it is like a micro tornado.
Yes.
Yeah. Okay.
It's I mean, it's happening everywhere. That is the point. That this phenomena of turbulence, we all know it like in a river or something, but it's happening everywhere. Everywhere we look in the universe, the matter, the fields, they're all making some turbulent movement. And the problem is that this turbulent movement is creating new features that you wouldn't expect that from those more basic principles. So that is some novelty we still don't understand. The turbulence is something that was from 19th century was explored. Even Da Vinci was drawing all these eddies and turbulences. He was obsessed with that. You could see in hair of his figures, in paintings, that he was replicating those eddies. And so we are defining this as some irregular motion. But the nature of this irregular motion was described by the beginning, let's say, of 20th century as in terms of statistics. So we don't know the details, but statistically there is some pattern, some behavior that we could recognize. So, for example, the work of Kolmogorov and some other researchers that, for example, saw that there is some, in most cases, there is some cascade where energy is transferring from big eddies to smaller eddies. So when you make a movement of fluid with your hand, for example, in a bath, then it will make a big circle, and that big circle will create smaller circle, and that smaller circle will create smaller and smaller and smaller, all the way to the what we call the level of dissipation. So, and you have this downward cascade where energy from this big eddy is transferred. And for example, this energy transfer is something that is statistically known or modeled in a decent way. However, there are some systems like, the first time when you saw weather forecast and they said that it will rain, and it was a nice sunny day. And the reason was the turbulence, because it's extremely hard to model the turbulences in the atmosphere. So that is connected to the chaos theory, where you have some small disturbance in the atmosphere can create a tornado on the other side of the planet. So that's why these systems are highly, we call it non-linear, and so you cannot easily or at least you cannot do some exact mathematical calculations to calculate how this pattern, how this behavior will develop. And this is hard. That's why when they're building cars, for example, they're putting those
to account for the turbulence.
Yes, they're putting them in a wind tunnels where they're doing this manually. They're sticking those
and trying out, let's try this way, let's try this way.
So that means that we don't have a proper theory, but we need to do manual testing to see what design is good and what is bad. Or we do
I imagine they do it for planes also manually.
Yes, I mean they're doing only partially, so they're taking only part of a wing, but you can do that in a real wind tunnel, or you can do it numerically. But numerics is also problematic because you have always a finite resolution in your computers. So you cannot go indefinitely with the resolution,
unfortunately.
And the problem, like I said, even small effects can create something. It's bigger later, and if you
tiny eddy becomes a huge tornado.
Yes, and that is especially visible in two-dimensional systems. So in three dimensionals, what we know, at least what I know so far, is that most of turbulences are following the downward cascade. So you will not see the vice versa,
Okay.
that the small eddy is creating a big eddy,
Okay.
especially in average. But in two-dimensional systems like the atmosphere, which is much wider than what is thick, is a huge problem because it can create. So it depends on the dimensionality of the system. So, and all these questions are also important in the universe. So, because they're playing an important role in creation of galaxies, in creation of a solar system, because these are all always some turbulence going on. And also, for example, in my specialty, high energy cosmic rays, there you have turbulent magnetic. You cannot easily deduce the direction from which these cosmic rays are coming from.
And how does one even start tackling such a topic?
Well,
I mean, what would be the final result? Like, if you would like to have a mathematical formula of perfectly describing turbulence, or what's the end goal? I mean, of course,
well,
you would like to predict everything.
That is a good question. What is the end goal? The end goal, in a broad sense, would be to understand better the phenomenon.
Okay.
But how to understand it? If you say, I want to do it through some exact mathematical equations, maybe you're so, for example, if you're enrolling into a PhD program and you say that I want to find an exact, maybe you're stating a goal that cannot be achieved.
Yeah.
So you can, that would be nice. That would be really nice that you can calculate.
They would slap you in the face.
If you can calculate those stuff, but I don't know. Maybe I think that we are missing some pieces of math and general understanding to tackle these problems. So it's more like there are, you can even if you find a solution of Navier, if you answer some questions regarding the Navier-Stokes equation, which is describing fluid motion, then you will get $1 million. It's one of those millennium problems in 1 of 7. One is solved, so, and one of these is the problem of, let's say, mathematical expression of turbulence. So in that sense, there is a huge interest into this problem, but for 100 years we didn't come up with some novel ideas.
Yeah, because we make planes fly, so we don't care how they fly.
Yes, but I mean, if you would solve this problem, I think that it would have huge economical consequences, because you could build.
But we have technology to correct the weather. We don't need to predict it. So.
I mean,
if it's raining, you make it stop raining. I mean, that's
but for example,
technology.
I mean, if you're a car designer, they're never making too big changes in the car shape or airplane shape because
it works.
Because it works.
Yeah.
I mean, but maybe there is some crazy new design which would completely change the way how we go through the fluid, like through air. And in that way, if you could anticipate from the theory what is going on, then I mean, first you would be rich, I suppose.
Yeah.
But then, and you could explain many other phenomena, both on Earth, on the here and in the universe. So I think it's one of the universal problems which is worth of at least thinking of. But of course, it's these are problems where you cannot easily come up to join into this game of publish or perish.
Yeah. Is there? Do you know of anyone who is currently tackling that problem?
No, there are people. For example, a lot of people are investigating turbulence in solar magnetosphere and solar wind. Why this is important? It's in NASA is NSA is financing this research because we want to have something what we call solar weather forecast, so that you know to turn your satellites to lower your planes on lower altitudes, so that they can reduce the damage from the solar activity. And for that, you need to predict how those how the solar activity will behave and how the solar wind will blow, and this is all connected with turbulences in magnetic fields. So there are a lot of research in these special fields, but which you can do. For example, I work on such specific things, but I'm thinking in parallel of those fundamental questions. Okay. Because you cannot say I will, like, for 20 years I will think only of these fundamental problems, because
you have to do something that you, can actually be done, and then in the background tackle the bigger problems. I mean, because obviously you go into physics and study it to tackle the big problems.
I mean, I think that we all somehow want to do that, but unfortunately it's...
Is this the guy you share stories with him in the bar? Yes, it is.
That is from the first streaming that we had.
Okay. Yeah, we can remove the sound of the chess pieces a little bit. I'm gonna leave it a little bit so not to make it too loud. Yeah, I usually make it so it's manageable, so it doesn't. Yeah, but now okay, there's two of us and we're not talking directly at the microphone, so I imagine it can be a bit too much. Gravity keep the Meadow on the couch. Yeah, gravity is currently preventing Meadow from going up on the couch. All right. I solved the gravity in my poem. All right. Send it to me via email. I will read it in the next video.
Can you go a bit up? Let me see.
Up.
Yeah. Is there something?
No, this is good because I've read that book by what's the name? I forgot.
Quantum Entanglement.
Yeah.
In simple words.
Yeah, and his entire book is about basically explaining quantum entanglement in simple words. But I can't remember the author. But you know him. He's a really famous physicist.
I can explain what quantum entanglement is, but I don't know if it will be simple. Okay, but let me try to think.
Okay, first explain it any way you can, and then we can dumb it down.
So quantum mechanics have some unusual properties. So we always in physics want to describe dynamics of the system. And the main tool in quantum mechanics is the wave function. So we describe all players in this game with a wave function. And this wave function we can describe the dynamics of this. So, for example, in non-relativistic quantum mechanics, it is described by Schrodinger's equation. So it says how this wave function will evolve.
It will always collapse, yeah?
No, I mean, how will it evolve through time? And then you can explain also how several, let's say, pieces, like, for example, 2 electrons, what will be their wave function. And what quantum mechanics is describing is that these objects are, when they were somehow in interaction, they're staying connected. They're staying connected, and even if they're not anymore close to each other. So one object, like one electron, can go to the one side of the universe and the other one.
Yes.
And we call them that they're quantum entangled. So they're somehow connected. And so quantum mechanics says that when you observe one object, then you're changing this wave function. We're saying that, for example, in Copenhagen interpretation, that there is a collapse of wave function. And that means that also, because those two objects are described with one wave function, that there is also a collapse of the other. There is also some change in the other object at the same time, despite the distance.
Yes.
So the nature of this phenomena, of this collapse, is something that is described, which theory is not saying what is going on exactly, and we need to interpret that. And so there are different ways how you can interpret this.
Yeah, I like the one where every single entanglement creates a parallel universe, because it's the only way sort of to explain how this one has an upspin and this one has a downspin.
Yeah, I mean, I don't like this interpretation because philosophically it's too expensive. I mean, to explain something to create infinite many universes, I mean, it's against an Occam razor, for example, the principle where you should say the simplest solution is something.
Yeah, but maybe to the universe this is the simplest one. Who knows?
I mean, it could be, but I mean, whatever, we are learning stuff constantly from nature, and we never observe such a, let's say, craziness in it's probably something more subtle, which we still don't have terms or understanding, than just conceptually creating. I mean, where all this matter in all these universes are coming from. I never understood this interpretation, because if we need to go to this many world interpretations, maybe many minds is more, let's say, rational than many worlds interpretation, where you have infinitely many everything at every observation. And also that is the question, what is the observation? I mean, there is some improvement. I was doing that, but that was a long time ago. Decoherence is a phenomena. So, for example, everybody knows the Schrödinger's cat thought experiment.
Yes.
I mean, I can repeat. If you have some system like a gun connected to some quantum system, and with quantum system, you don't know, it can be in both. It can be in two states at once, and so these two states are connected to a gun, and that gun is pointing to a cat, and cat is closed in a box. And so if you correctly connect all these equations and entangle those wave function from atomic system to a gun to a cat, you would see that, you would conclude that the cat should also be dead and alive at the same time. However, when you open the box, it's not.
Yeah.
And also it can be somehow both dead and alive. Maybe it should collapse into this state, but we don't know how it should look like. And the reason why this is not happening is partially explained by decoherence. And decoherence is a process where you have many people ignored the fact that systems are not perfectly isolated. There are always some kind of interactions, and those interactions are actually connecting with those atomic system, with that gun, with that cat, and all these connections with the environment are creating that total wave function is predicting only certain kind of outcomes. So not every outcome is possible. And that is the process of decoherence, where you're decohering the coherent state. So these are and partially it's explaining the problem of Schrödinger's cat. However, there are still some there are still some unanswered. So it's not answering. It's not answering the question: what picked which state? So is it dead or alive? But at least it's not that we are totally unaware what is happening. So there are still space for interpretations, but I think it's making some constraint on interpretations that. I mean, in that context of decoherence, I think that many word interpretation is even less attractive.
All right. In other words, it is impossible to explain quantum entanglement in simple words. No, because in this book that I've read, he also claimed that he will now explain quantum entanglement in simple words.
And he introduced the many worlds.
I've already he introduced all of the theories, but I went through like already like 100 pages, and it's still building up to that moment of clarification where you will explain quantum entanglement in simple words. So basically, he wrote a book on it, but I don't think.
I don't know. I mean, if you give me some time, I will try to. But I mean, first, I don't do quantum mechanics regularly, and these are stuff that I did many years ago. So I need to recall a bit, refresh my memory, and maybe for the next time I could come up with some better explanation that
no, because what I remember from the book and what sort of to my limited understanding of the topic makes sense is that if you had if you like fire electrons at completely different directions, and this one you send this one to like a different galaxy, and this one remains here, and then you observe this one, and you will see, let's say, an upspin.
Yeah, so the spin should be conserved.
Yeah.
So the other spin will
be
the other.
But it will be instantly there, even though you will not be able
to... Yes, that is called a spooky action at a distance.
You will not be able to confirm it because, the information traveled faster than light, but you will not be able to confirm whether it really traveled faster than light, because how will someone tell you it traveled there faster than light?
The problem here is that you cannot communicate in that way, at least not naively, because you cannot transfer an information. You cannot transfer information because you cannot choose in which direction you will collapse the electron state. So you cannot transfer information, and so there is a sense that you could escape this saying that no information can travel faster than light. No information can travel faster than light, and other things, I mean, phase velocity, group velocity, for example, or something in physics, you can make travel faster than light, but these are not means of transferring information.
So what is the simplest way to explain that? He said, there's you here and Petar in the other galaxy, and you observe it in the same time. You see an upspin, he sees a downspin. How did the information travel?
No, so I'm you mean the connection between those two?
Obviously, that's the spooky example.
Yeah, that is called spooky action at a distance. I think it's this is the phrase that is used.
And that's why sort of that's how I understood why it the simplest way to explain that would be to introduce multiple worlds.
But this,
Yeah.
I think it's still expensive. I mean, to introduce multiple worlds just by not knowing a better answer than this, it's like
It's the lazy way out, yeah.
I don't know. I think it's first, it's definitely something that's formalistic. You would see equations, and the easiest way to interpret those equations would be, let's say that all states are possible, and that all states not possible, but that all states are happening, but only in different universes. But I don't know. I just cannot philosophically comprehend this, because I mean, why would be so
But what
many?
are more physicists in the world? Are they leaning toward many worlds, or are they leaning towards other theories?
So I think that the most of people are not thinking about it. So they're just using that interpretation that is called "shut up and calculate."
Yeah, okay, okay.
But however, it was already like, I don't know, 10, more than 10 years ago. I was reading some results on some conferences about interpretations, and that they're like people who are studying these things of interpretation. There are a lot of people who are supporters of many world interpretation. But I was really trying. I was trying hard to understand this, and only judging from mathematical perspective, it's not enough for me to because I mean, of course, you're making it mathematically elegant because you don't need to assume any collapse, because there is no collapse.
Yeah.
But still, I mean, it's totally crazy.
I don't know. I really liked it.
I mean, it's okay for all these science fiction movies.
Yeah. All right, let me just check real quickly. Where did
Whoa.
we left it off? Okay, sorry.
Oh, there are
Let me
really
just
many
check.
questions.
Okay, this is the poem. When yestereve the moon arose, then I fancy it about to bear a sun. So broad and teeming did it lie on the horizon. That is beautiful, Timothy W. Shaw. Very nice. All right.
Let me see.
Sorry. Yeah, this is we already made the introductions, but you've joined quite late. This is Andrej Dundović, physics PhD, and we had another gentleman here who helped us, discover great secrets of the universe, but he had to catch a train.
He answered already all these questions, so I'm just now doing the ending.
Maybe you can understand this? Is this actually a question? What do you think to our Earth's sun, the actual Earth itself, beginning as a sun?
I don't know. I mean, I don't. So, what does it mean to be a sun? If it means to, if the question is about whether a planet like Earth can produce enough of thermonuclear reactions to
become a sun,
to shine like a star, then the answer is no. It can this planet is too small to create.
Yeah, I mean, obviously.
So I think that our Earth sun. I don't know if that is.
No, I don't think that's what he meant.
But maybe, I don't know. So we are all created from a material from previous stars.
Yeah, from previous supernovas.
Supernovas. So all these heavier
elements. So yeah, it does come from the sun, just not this sun.
Yes. So in that sense, I would say yes.
Can you make anything of this? What do you think about the new team of NASA investigating the unidentified anomalous phenomenon? I don't even know this word.
What? No, so
I think it's a question regarding extraterrestrial life.
So my personal opinion about this is that, of course, that there is some kind of life
Yeah,
out there, but it depends is how we define life. It's really hard to define what life is, and and how should it look like.
Okay, so you don't necessarily consider it should be carbon based. It could also be just maybe
No, I mean
pure energy.
It's really hard to put a line where life begins and what is unliving matter.
Yeah.
So what do you say? This, for example, for viruses or something, they say that they are like particle wave. That
I consider them very, very much alive.
So the thing is that it's really hard to define first what life is, and then it's really hard to search for something what you haven't been what you don't know how to define.
Yeah, okay, but you're not looking for life. You're looking for any form of recognizable intelligence, like anything that.
And what is intelligence?
Okay, you find something in nature that nature cannot produce. Maybe
but we are product of nature, for example.
Yeah.
And we can say that we are extension of
Yeah.
nature. But okay,
Yeah.
let's say that I don't know. I think that maybe intelligent civilizations to achieve that level of, let's say, space travel are socially so advanced that they will certainly not behave on patterns that we observe, and that we think that how would that extraterrestrial life would be the same as our life, as our society, only that they will have super fast, faster than light spaceships. So they will also.
Yeah, we think that they will be traveling at warp 3 and also drink beer.
Yes, and also they will have same ideas and same concepts. Like, I think it's really hard to anticipate that, because we know that from theoretical point of view, we are so far from space
Exploration.
So with anything that is even resembling faster than light traveling. So I don't
but
know.
it always. I mean, I always remember that in USS Voyager, you know, the one that
Star Trek.
Star Trek Voyager, the one with Captain Janeway. They waste like 70 years or something trying to get home, but they've never even left the Milky Way galaxy.
Yes, I mean,
No,
but
They
people,
have like maybe a few sectors, you know.
maybe I should clarify something, that people always think that when you look through a telescope, that's what usually visitors are saying, asking. When we show them planets or something, or the moon, they said, okay, can we look at that star? And I say, but if we point a telescope to that star, you will also see just a star. You will not see any circle or any sphere, because it's so far that it's still just a dot.
Yeah.
And so I think that this is just saying that the universe is so vast, it's so big that I don't know. I think that we are pretty much alone in this corner of the universe.
Yeah, even if there, I mean, there should be life, but if there is, there's no way of ever knowing that.
I mean, imagine just going to the closest star. What the closest star is, Proxima Centauri. So it's like 4 light years away. 4 light years. And I mean, if you have like a really fast spaceship, which is going 10% of the light speed, what it will take 40 years there. So it's totally, but we cannot even reach this 10%. But I'm just saying that even to reach the nearest star, it's
Yeah, could we perhaps launch a ship carrying, like, I don't know, maybe 1,000 people that are not yet born, and then program it so that they will be born, let's say, in some, how long would it take to travel for light years?
I mean, I think that in principle it could be reached, but the thing that technological advancement, it's not just like going to the moon. I mean, going to the moon is hard. I mean, you could see that now.
Yeah.
We are preparing for years to again visit the moon, and to go to the Mars, it's already much harder. So when, I don't know, people are saying we just need like a few years to reach Mars, I think, I mean, all technological advancement that we have is still not nearly enough to do so, especially to do so in a safe way. Of course, you can launch people, but like they have like 15% to survive. It's not something that you could say that you could call a success. And the more distant, the more you travel further, the problems are going. I mean, they're exploding in terms of technological requirements.
Yeah, it wouldn't really make sense. Even if you launch something now, at the point it reaches it, we will have technology that is so much better that will probably just reach it even faster.
I mean, I think it's these all questions are really nice to make sci-fi novels. It's, you can speculate, and but I cannot. I mean, all what I say are just speculations.
Yeah.
Which we can make better or worse, but I don't have a strong opinion about this.
Okay, more of the poem. Not by wrath, but by laughter do we slay. Come, let us slay the spirit of gravity. Okay, please send me the entire poem on the channel. I will read it at some video. Sounds really nice. Okay, sorry, Bruno left us. Okay, let's check out one more. Let me just check if there are some nice Is there, okay, this looks like a fun question as always. Is there something physics recognizes that cannot be solved? Not that we don't know how to approach it, but that, okay, obviously everything can be solved.
I mean, it's okay. It's a good question because it's a more philosophical question in a sense that uh, uh, physics, of course, cannot answer those questions which are outside of its realm. So, in a sense that there are some questions which are like saying, how can we know? How can we even understand the world around us? Where those basic concepts like space, time, matter, energy, where they are coming from? These are not something that physics, at least the physics that, how we defined it, can answer. However, the assumption is that, of course, the older disciplines where physics was came from is philosophy. Philosophy should and is tackling these questions. Of course, there are no easy answers, but I would say, for example, that okay, this is for philosophical assumption. Let's say that we are part of some absolute, some one. So if we are coming from matter and there is no like external spirit or something that somebody put in our bodies, then I would say that we should somehow understand the world around us because we are of the same.
Okay.
So if we are of the same,
Oh, if we are
we should
if we are created, maybe someone put a limiter so we
Yes.
cannot go beyond this point.
So if you are, if there is, if we are all of the same matter, of the same or spirit or whatever, then we should understand the world around us. And the fact that we are making sense of the world around us is giving us a sign that maybe we should proceed. I mean, that there should be no limit of understanding the world around us. So I think that there is no questions, at least that people in principle cannot find the answer. The only thing is that we would always find new questions, and I think this process.
Yeah, but it's like
exemplary.
what's the name of those the Kardashev scales, or it's like the like you have the generation 1 that achieves this, then generation 2 achieves this, then generation 3 achieves this. At some point, you can use Dyson spheres to harness energy. Like he makes sort of a step by step into and we are at maybe 0.1 of that scale. I don't know what's the name of the scale. I forgot. I think
No, but these are like concepts of Dyson spheres or something. But I mean, for me,
yeah, but even no, what I was trying to say is even if we were at the top of this scale, we would still have the same questions.
yes, but I think that we will always. I mean, the nature of question will be different. I mean, maybe it will grammatically be the same, but we will think differently about these questions
Yeah.
than today. And I think that there is no end of this scale. Like the universe itself, there is also endless progress. Let's say that we could asymptotically reach are reaching some understanding, but there is never an end. Because I mean, it would be funny.
If there was, it'd be like, what's to keep us from advancing further? Okay, this way you always want to reach this.
Yes, but imagine I'm always against some special moments in the universe. Like saying that we will reach a point where we will know everything. I mean, you see how it's absurd it is. It's like then the universe will say, "Okay,
You win.
you win." This is the. I mean, I don't believe that.
Now on to the next one.
I think that the universe and matter and nature will develop as we go along, and it will develop new features and new things that we will never find the final answer in that sense, and we will say, okay.
But isn't that weird? I mean, what's how is the who made like what? What is this?
Well, these are really tough questions, but let's say that I think that we are a lot of when we are talking about natural laws. When you think about it, it's weird. Why it's weird? Because that means that there are some laws, like on some uh, blocks or written somewhere, where nature is looking how should I behave according to these laws, so that they're written somewhere, that there are somehow externally prescribed on nature, which is like only following these deterministic rules of the game. And it is implicitly introducing duality in our concept. That means that there is some laws which are out there, and there is the players which are following these laws. And again, it's philosophically it's weird, because you need two stuff that are separated, and then you have even more questions. Why these stuff are separated?
Yeah.
Who created this stuff, and why this stuff? And here, if you try to bring them together and say that those behaviors are imprinted or are inside the nature itself, and that nature does not know on from start where it is going. It's developing in its own, and it's making new rules. I don't think that nature knew, or anybody knew at the beginning, for example, in early universe, that I don't know, I will drink this water. I mean,
Okay. No.
or that there will be even water, or that there will be some organic life on Earth.
Okay, but that's basically the definition of a predeterministic universe. So it cannot be predeterministic.
It cannot, but also it cannot. You cannot even know the rules of the game. So you see that in physics, the lower you go from energy, when you go to lower energies, you get more complexities. So the higher the energy, stuff are more simple. And so when the universe when the universe was cooling down, it was introducing new complexities. But so that the question was, if there was some laws, it knew that in, I don't know, few million years, the things will develop that way. But if you say that there were no external laws, but there was just some play of matter that was developing, so it was like something more spontaneous, something more live, let's say. It's more, I would describe that when we now return to this question, the origin of life.
More turbulent.
More turbulent or more alive, so that matter and philosophically, it's more alive than we consider it. And then there is no question how life began.
Yeah.
Because it was always there in some form. Just we are making some unnatural boundary and saying this is.
Yeah, because we want it to appear more like us. Sort of all right, let me just check a few more as we are nearing the end of the tournament. How many? Okay, we do have 15 more minutes. So Rage Hunter still in the lead, very nice. Followed by Shankare Peaches and Bruno Pavlović in third place, but he obviously withdrew or rage quit, as he did lose 2 games, so I guess he didn't like that. So yeah, let's continue checking up on the games while we take a few more questions. Maybe you spotted. Okay, still.
Some advice for someone who will study physics this autumn.
Okay. But for which grade? I mean, for preschool.
No, but I can generally answer this.
Okay.
Just try to have fun with that.
Fun.
That is, try to find a reason in itself in this topic, not to.
But it is. I mean, it is one of the greatest topics to enjoy. It's just. I mean, if you have a professor in school who makes it super dull, or maybe.
Yes, I mean, I think that generally with physics is easy to motivate people. Why? I mean, you just.
Okay. Math is the problem.
Math is the problem, because math in principle is like those games with simple rules, and then people are like they don't see fun in that. But I think that also math can be motivated to look at it, to be more interesting.
Yeah, I don't know. It has always been one of my great desires to study math, but I never could do it. I still hope
Maybe that's why you're studying chess.
I still hope to at some point start with math, but I don't know when that will be. Probably, later on in life. Mr. Figo is asking, have you studied in Italy? How would he know that?
I've been on a postdoc in Italy.
And you've
I liked it.
you've avoided the earthquake, yeah?
No, I came. I've been in L'Aquila,
Uh
and I pretty much liked it. It was really nice. I like almost everything there.
You've been in Calabria as well.
Yes, I've been there. Actually, 2 times. I
Yeah.
visited a friend there.
One of the greatest chess players ever was Gioacchino Greco. Also, they called him the Great Calabrese. Basically, I mean, everything we know today comes from him.
Really?
He was the first one. Yeah, I mean, really a legend. He was. I mean, because back in those days, you could. No one played chess. The chess was a game of chance, like dice. And he was the first one to have he knew 100 checkmates by heart, and then he would play for money. And even though everyone thought like he was gambling, he wasn't really gambling. He was just scamming people for money because he was really good at chess, and that wasn't the thing. No one was good at chess except Gioacchino Greco.
When it was?
That's like 1600, 1500, maybe. I don't know. I think he died like 1590 something. But yeah, he really he made so much money on chess. Like, a really unbelievable guy.
Nice. I didn't know.
Yeah,
that.
that's why I thought. But you only said that you were in Calabria after you already left, and
No, I've been once. I've been twice actually. Once I went for to visit a friend, and the second time I was crossing Calabria to visit Sicily.
Mhm. I was wondering maybe if there's like a cool statue of him or
But
something.
in which city he lived?
I don't know. I don't know. I don't know if it is even known. I will have to check. I've never done like a real research on him. I thought chess would make me smart, but I can't understand a word from this guy. Yes, it is a bit different. Gravity is annoying. Am I right? Have we found aliens yet? Have we found anything? Is there any knowledge of anything?
I found half a cat inside the box. Okay, that is nice. I mean, but that is great that science can also introduce some new imagination, because I think that science alone cannot bring always new ideas. Sometimes new ideas are emerging from other fields like arts or something. So, for example, I always recall that I saw that before Einstein, some artists were questioning. Some artists were questioning the concept of space and time, the relativity of space and time. So the idea actually emerged in some people's mind in arts before it was scientifically built. So I think that's
but it's from that's how I understand it works. I mean, first art discovers it, and then technology makes it, and then new technology is used to create new art, which inspires new technology. Sort of this correlation between science and art throughout, since the beginning.
yes, it's interconnected process, because sometimes you cannot advance in understanding something without proper technology.
Yeah.
However, also there is you get some inspiration from art, because it's those terms like whenever in any field of research, especially what I know in physics, is actually all these problems that you're encountering are always somehow doing has some are relevant with some basic concepts. So it's not that problems in science are like somebody needs to calculate this correctly. I mean, of course, there are many technical questions like this that people are doing, and that. But whenever you encounter some a big problem, the answer is never like a technical. You just need to solve this correctly, and you will find the answer. It's always like you did something conceptually wrong way earlier. So, and to find new ideas, maybe you should look elsewhere, not just trying to repeat this process of doing, I don't know, calculations all over again.
Yeah, makes sense. Who is Andrej, the guest speaker? Yes, Andrej is the guest speaker. Is there a branch of physics concerned with artificial intelligence?
Yes, I mean it's a branch of physics.
Yeah, I don't think so.
Let me think. No, I mean,
is AI currently being used some in the realm of physics to explore anything?
Yes, I mean, for example, I've been on some conferences where people were saying, for example, in high energy particle, for example, in accelerator physics, particle physics, like the physics that is done in CERN or Fermilab, they have this problem of making bigger and bigger accelerators.
Obviously,
of particles. And the thing is that when you're colliding particles on higher energies, you're creating more and more secondary particles.
Yeah.
And the problem is that you cannot record on really high energies all these particles, and you need to introduce in all these detectors around the collision site, you need to introduce
AI to eliminate most of them.
Well, first they introduce some triggers, like they will not detect this and that, and even with all these triggers, they're having a lot of data. Petabytes of data are produced. I don't know how often, on which frequency in those experiments like CMS or Atlas in CERN. And now these days, when they want to go to even higher luminosities, so that collisions are more frequent, they need to introduce those machine learning stuff, which are then trying to decide which data is relevant, so that they completely ignore most of the particles that are coming from the collision, because there is just too much data for it. But I don't know, I'm skeptical about this, because machine learning is, for most, it's generally a black box. We know in principle how it works, but sometimes results surprises us. And the question is always whether you will introduce some bias in the process. Will you get what you expect from these new triggers that are enforced with machine learning?
So you have to first create proper triggers in order for the machine learning to actually be useful.
No, I mean, you're using triggers which are trained with machine learning algorithms, so that because you cannot decide anymore on some mechanical level whether you will get that data downstream to the hard drives and computers.
So basically you will use AI where you have large amounts of data.
You will use machine learning. So I'm not using AI, because AI is just too broad.
Too broad, okay.
But I'm using this term machine learning, although people are using this interchangeably, So you'll use machine learning to trigger to discriminate between the data that you will record and that you will discard. So you will have these algorithms on the detector itself, so that you don't even record much of the data.
Yeah.
And so if you do it incorrectly, you will introduce a bias.
You will not find the graviton.
Certainly.
Yeah.
Okay.
All right. So there you have it. Okay, still with the poem.
Okay, let's. But okay, I mean, we were maybe not doing this for what?
No, but that's
2 hours.
Yeah, but that's, I think that's considered brief when discussing things like that. Okay,
Yes,
he says, what does your friend think of the Tunguska event in 1908? But that's, I mean, is there anything to think about that? Isn't everything known about the Tunguska comet?
I think it was. I don't know. I'm not an expert on that, but I thought that it was an explosion of meteorite, right?
Yeah, that's how I know it. Yeah, I didn't think there was any mystery behind it. Like it, as I understand it, but it didn't hit the Earth. It like blew up in the atmosphere, but it still scorched everything.
Yes.
Yeah, so that's how I remember it.
Oh, I don't know, but I never thought it is a. I mean, certainly there are somebody who is studying this phenomena or this event. Maybe there are some questions, but in general, I didn't hear that there are still some, like, that we completely don't know what happened.
Yeah. How many dimensions are there? Is there a short answer?
4.
4. Not
so far.
Not 11 or 13.
So far, I'm voting for 4. That is the question for string theorists.
There we have it. Greco was born in 1590, 1600. Okay, so it's obviously not known when he was born, and he died 1630. So he died at our age. What is this? Group theory is a very complex subject.
What can the nature of solar system or galaxies be governed by the principle of natural selection?
Oh, that sounds like a big one.
But I don't know. Let me think about it. Can the nature of solar system or galaxies be governed by the principle of natural selections?
Yeah, I mean, I understand the question, but
no, I'm thinking first. Natural selection. So it depends what is meant by.
Yeah, I don't understand the nature of the solar system.
No, but I also I'm thinking. So can you? No, you need to have some. To natural selection, you need to have some environment, of course, which is selecting those which are, let's say, better fitted for this environment compared to those which are less fitted for this environment. And in that sense, I would say yes. There is always some process which are eliminating those stuff which are not fitted for that kind of environment. So I think that, for example, early universe was maybe a better environment for one type of galaxies or solar systems than this older universe.
Bruno has, okay, I will take one more question from Bruno because this is one I really like. thoughts on the fusion helium energy versus the tokamak. And where are we currently? I checked on the tokamak's progress like a couple of months ago. I don't know at what energies they are currently.
I mean, these are type of questions which I can only speculate on. Maybe people are generally who are. These are like really concrete stuff. I cannot answer those type of questions. Like I don't know. I would say that I know that there are many approaches to the, but not fission, but fusion.
Yeah, obviously.
Okay, so there are many
It's
approaches. To,
U is next to I.
okay. There are several approaches to fusion, and I know that the real problem is not to produce fusion. We can do that, I mean, for almost 70, 80 years.
But to keep it going.
No. But to make it more efficient than the energy we're introducing into the system. So that is the real question. Can you make a fusion process here on Earth that will give you more output energy in total than you introduce on all these, for example, shieldings, electricity, pumping the heat inside, accelerating particles. And that is, in principle, we know that it can be done with, because we have the example in sun.
Yeah. But he doesn't have to worry about keeping it cool outside because the universe is very cold.
The thing is that sun has a huge advantage. It has huge mass.
Yeah.
So it can create a lot of pressure, which we cannot achieve here on Earth. And that's why, since we cannot achieve such a pressure, we need to rise the temperature much, much higher. And for that, to keep that temperature and to shield everything from that, it takes a lot of energy. And you need to achieve that the total amount of energy created from this fusion will be higher than the energy
so that's the problem.
Yes, so this is the Q factor. So the ratio between output and input energy. And I think that, I mean, we are still below 1 in average and in the long term. So
shouldn't we focus on creating tokamaks in space other than on Earth? You know,
I mean, the tokamaks are something that I was briefly interested in, because there is also a problem of turbulence there.
Okay.
Because you cannot keep plasma inside a tokamak.
You use it with magnets, yeah.
Yes, you shield it with magnets, but you cannot, if it's too, so if they are following known trajectories, then they're kept in this enclosure, in this field. However, if they start to make turbulences, they can easily break the shielding. And so you need then to increase the field strength to keep all those even turbulent one. But then when you're increasing the magnetic field strength to keep everything inside in tokamak, then you're wasting more energy into shielding, and then Q is harder to reach. So it's also some fundamental questions like turbulence is kicking in this problem, because if you would know how to model this correctly, so how to avoid turbulences with these particles in the tokamak, then you could probably reduce the field, the magnetic field strength, shielding, and that would help you to achieve Q easier.
So they have unnecessarily bigger magnetic fields just because they
Yeah,
can't
so you see,
counter
all
the
these
turbulence.
things are really hard because there are a lot of engineering, a lot of technical stuff, but also a lot of unanswered fundamental stuff. So they're always projecting that the fusion is here, just around the corner, but we are just discovering how hard it is.
Yeah, but I think I've read like they were able to keep the fusion going for like maybe a minute and a half. Is that could it be?
Yeah, I think that I'm not so into this, so I don't know.
Ah, okay,
But
okay.
I read some headlines uh, that they managed, but they never answered then if they kept it to last for so long. Uh, what is the Q factor?
Ah, okay, okay.
So that is always
Okay, one short question, and then we are reaching the end of this great discussion. Do you study gas dynamics?
mm, I don't know actually. So is it something?
Sounds very turbulent.
No. I mean, I study dynamics of gas.
Okay.
Gas. That's true, but I don't know if there is something else
No, I don't.
meant by this. What is this?
Do you want to take this one, or are we done?
Which one?
Can you explain how inflation solves the magnetic monopole problem? The only place I've heard of the magnetic monopoles is in Big Bang Theory.
No, I wouldn't go into this direction because I would. Oh, so first, it's also these are some assumptions which are introduced to solve some other problems, and the magnetic monopole for me it's a problem that is artificially introduced some earlier in the game, so I wouldn't even
Okay.
talk about it because I don't think it's a problem we should start with.
Okay,
We should go a little bit back in arguments and to see where we needed to make this assumption of existence of magnetic monopole to start to talk about this because okay, but that's for some other time.
Is there okay now that he already asked the question? Is there a reason one should exist?
What?
Like
So-
should a monopole even exist? I mean, is
no,
there?
no. I think it's conceptually again something that I cannot force myself into this because in when you study physics, you really see how uh, electrical and magnetical forces and fields are united, and you see that due to special relativity and other reasons, I mean, just change in coordinates in reference frames, the magnetic field is a consequence of electrical field, and all magnetic fields are coming from some current of some currents or charges in motion. So I wouldn't say that if you ask me, okay, explain me magnetic monopole, then I would need to revisit all electromagnetism that I know in a sense that I don't need that practically.
Okay.
So I wouldn't talk about that. These are one of those hypotheses which are introduced to explain something, and I think that these are like expensive assumptions.
Okay.
So if you like what we said for many world interpretation, something, these are assumptions that I don't go into this direction.
Do you have any idea what the sacred geometry is?
No.
No, doesn't sound like something I've never heard of it.
I don't know. Maybe I know it under some other name.
Is physics basically applied mathematics?
No, because in physics you have some new content to deal with. So it's not only that you have mathematical equations and that you deduce everything from math.
Okay.
So you have some that is
Nothing can be discovered in math.
well, depends how you define.
No, okay.
But okay, for example, if you say that if do I believe that mathematics is already there or is it constructed by us? I think that the answer is that for me at least it's not out there, it is constructed by us, because like I said, there are no, in my opinion there are no laws outside, like
Yeah, this is something we use to make sense of things.
yes, but the math naturally emerged from our observation of the world around us. So it's not, it's a process that we invented, not discovered, but which is somehow really interconnected with our experience with the world. So in some sense, the math is also not it's not here generated. I mean, came from pure air. I mean, it's not came from nothing. Although, so
Yeah, because
all
there are constants in the universe, and obviously you can make something with those numbers. You know.
Okay, like pi or something.
Yeah, or like Planck constant, or like.
Okay, but these are different. So different are mathematical constants and different are physical constants. But I don't know. This thing about mathematics is hard. Maybe some people who are more into philosophy of mathematics and origin of mathematics could argue better. But I'm in those on that side that the mathematics is our invention. It's our construction. So in that sense, it's also our construction, like physics. So you cannot, and there are always some novelty. Also, in chemistry is not applied physics, and biology is not applied chemistry.
Yeah.
So it's not. I'm not in that camp of reductionists who will say that there is no novelty here.
Okay, this one says look up Randall Carlson Sacred Geometry. I will just save that for later to check it out. So thank you for that.
Okay.
But yeah, okay, we can pretty much end it here. We've been going for quite some time now, and something that.
So I can say a few words. So if you are interested,
yeah, I was going to mention that. Yeah.
We're discussing this type of questions on discussion groups here in our Cosmological Center. But if you would like that we bring those discussions more into this virtual on the internet, I mean, you could say you could express this interest by visiting either we started a channel.
Should we play the outro?
Okay, I mean we
can play the outro.
They're not so professional. You can show actually the video just.
Yeah, okay, I will show the video, but this is okay. I will give you a link to the channel in the chat if you guys want to visit it. There you have it. And also, once the video is published, it will also be the first thing you see in the description below. Okay, let me just.
Petar here in several videos.
Yeah. For those of you who joined us late, Petar already left. But yeah, okay.
To catch the train.
Yeah, their channel, Institute for Cosmology and Philosophy of Nature, is the first thing in the description below of this video. You can even click it now if you guys want to check it out. And now or later, but yeah, let me just quickly play this video just to get an idea of what's happening. There we go. Let me just make this a little bit louder. All right, there we go.
I'm Petar Pavlović. By profession, I'm theoretical physicist. I'm specialized in the fields of general relativity and cosmology.
Hello, I'm Andrej Dundović. I'm also a theoretical physicist. I'm working in fields of plasma physics and high energy astrophysics.
Our mission is to unite scientific work in physics of the universe with the popularization of science and with bringing modern physics to the general public. With this aim, we built this place that you see, which we call the Cosmological Center, and which has an observatory as one of its parts. In the last year, more than 100 students participated in our programs, including Summer School of Cosmology and Astrophysics. We also taught philosophy of science, general relativity, and quantum physics. Our desire is to extend our programs to reach the global audience.
We have specific programs for people of different backgrounds, elementary and high school pupils, university students, students of natural sciences, and people in general, just wanting to know more about the universe.
So, if you always wanted to learn general relativity and quantum physics and learn how does the universe function but never had an opportunity, or you're just an impatient student who doesn't want to wait anymore to learn more about the universe, contact us. We will listen to your interests and offer you the type of course the best suited to your needs, interests, and the level of knowledge.
Okay, so there you have it in short. What you can expect to find when you visit their channel. How many videos are there for people to find
I think
currently?
Four.
Okay, so you are.
Something.
If you join now, you will be there, as one of the first, and you will be able to evolve with the channel.
I mean, we are still trying right format because, like you see, it's not easy to introduce some concepts in like 30 seconds. So
Yeah.
we are trying to find a right duration of videos and how deep to go into explanations.
Yeah.
To be both correct but also to be understandable so that you don't need to develop all.
Yeah, I mean everything that you are discussing there is incredibly entertaining, but also you have to have an idea of how to present that to the people, because like I said, there's nothing worse than that professor that makes something that's incredibly interesting super boring. Which is not easy to tackle. Different people require different means of being entertained, so you're in for a challenge, but I mean that's why you are into physics.
Let's see.
All right, so
Okay.
and that's it for this. Let me just quickly read who won the Universe Arena. The Universe Arena was won by FIDE Master Rage Hunter, so congratulations on that. Second place, Shahanda Pereches, sorry I cannot read that. Arkadito Duta in third place, Ratahmas in fourth, then we have Bruno Pavčević in fifth. He was doing really well, but then he lost 2 games and then just decided not to continue. Shah Borca from Serbia in sixth, Muzard in seventh, the Don Machiavelli in eighth, Alan 7 on 7, and Mr. Cookie 2015 in 10th place. So those are the first 10 places out of 360 people that played. So big congratulations, and yeah, hope you enjoyed this. Thank you, Andrej, very much for joining me.
Thank you, and thank your audience for
Yeah, I'm
patiently
sure.
listening.
Yeah, I'm sure
Thank you.
they've enjoyed
And
it.
for asking all these questions.
Yeah,
It was really nice.
we've discussed about repeating it next time with Petar being able to join for a bit longer. So, you know, prepare some very, very difficult questions for next time so we can really, really go into it. But yeah, anything you would like to add?
No, I mean, until the next time.
Yeah, yeah. So, like I said,
have a nice evening, day, or
yeah, wherever you are, and yeah, if you would like to learn more, follow their progress. First link in the description below. Join them on their journey to, you know, sharing what they know with everyone else. Thank you all, and we will see you soon.
Thank you.